Congratulations on completing the last exercise and on writing a code that calculates an integral using Monte Carlo and that also determines an appropriate error bar on the estimate of the integral that you've obtained. To be honest, I could have stopped this exercise here. You now understand how we can use Monte Carlo to calculate integrals, how the estimate that we obtain for our integral is a random variable, and how we can extract an error bar for this estimate. This is probably sufficient for the rest of the module. Having said that, however, calculating error bars using resampling is computationally expensive, and it is therefore useful for you to learn a few other cheaper methods that we can use to calculate these confidence limits. In the final task of this exercise, I am thus going to teach you about a method called bootstrapping. While the next block the exercise, I am going to teach you how we can calculate confidence limits by using the central limit theorem. Before we get onto that, however, let's first briefly review what we have done thus far. We've been learning how to compute integrals using Monte Carlo sampling. In other words, we have been learning how to calculate the area under a curve like the one shown here. A function that uses Monte Carlo to calculate this integral is now shown on the right-hand side of the slide. This function works by generating pairs of uniform random variables that lie in the rectangle with base length b and height a that is indicated in the diagram. Multiple pairs of these random variables are computed, and the number that lie underneath the curve is counted. The final integral is determined by taking the ratio of the number of points that were underneath the curve to the total number of points that were generated, and by multiplying this ratio by the area of the rectangle, as in the formula that comes after the return statement in this function. During the last task, we acknowledged that the estimate of the integral that we obtain by applying the method shown here is a sample from a random variable. We thus asserted that as well as quoting a value for the integral, we should also endeavour to characterize the distribution from which the value for the integral we obtained was sampled. With this in mind, we therefore wrote Python code to run the function shown here that computes the integral multiple times. We then calculated the sample mean from all these samples, as well as the 5th and 90th percentiles for the distribution of estimates that we obtained by sampling. By computing the 5th and 90th percentile, we stated that we had computed the 90% confidence limit on the distribution of values we could obtain for the integral. In other words, we had calculated an appropriate size for the error bar on the range of values we could obtain for our experiment. There is a massive problem with resampling, however, namely that it is a very expensive technique for computing the sample error. We have to generate multiple samples for the sample mean, and each of these sample means is computed by sampling a set of random variables. To generate the mean and confidence limits using the code on this slide, I would have to generate 50 million pairs of uniform random variables. For many of the numerical experiments that I want to perform, generating this number of samples is not computationally feasible. We thus have to find a cheaper approach. In terms of getting something cheaper, we can make progress by recognizing that this quantity here, tot in over n, is the sample mean for a Bernoulli random variable. Each pair of random variables is either under the curve or not, and thus this quantity that is added to tot in each time we go through the loop is either 1 or 0. On top of this, the ratio of the area under the curve to the total area is fixed, so the probability of getting a 1, i.e. the probability of generating a point that is under the curve, is the same every time we generate a pair of random variables. This probability, this probability is just A, the area under the curve, divided by A times B. The cheaper method, known as bootstrapping, that I'm going to introduce here for calculating the error, takes advantage of the fact that we're calculating the parameter of a Bernoulli random variable. What we do is we assume that the value we obtain from our first run through the function is the value of the integral. More importantly, however, we also assume that the quantity tot in over n is the exact value of the sample mean for our Bernoulli random variable. This assumption is useful because it ensures that we can resample from a Bernoulli distribution instead of sampling from the true distribution again. We then generate our resampled sample means using the code shown at the bottom of this slide. If I point out a few things about this code, it will hopefully make what we are doing with this bootstrapping method a little clearer. Firstly, notice that the quantity called mean is computed by the function ratio that is shown at the top of the slide. This quantity is thus our estimate for the ratio of the area under the curve to the total area of the region we are sampling points from. Then notice that the if statement ensures that we are sampling Bernoulli random variables with this parameter. The inner loop in this double loop is generating sample means for this Bernoulli random variable. Notice also that the same number of samples are taken when we compute this sample mean as were taken when we computed the quantity mean by generating pairs of random variables and testing whether they were within the integral or not. In other words, the way we generate our samples here is very similar to what we did in the resampling code. The only difference is that now we are generating new samples by sampling a Bernoulli random variable. In the previous case, we were reperforming our numerical experiment. Once we've generated our set of 1,000 samples, it should be clear to you how to proceed. As always, we get confidence limits on our estimate of the mean by sorting the list of samples that we obtained and by extracting the elements corresponding to the 5th and 95th percentiles of our sorted list. The only difference from the previous code is that we need to multiply the values that we get out for the percentiles by a times b in order to get the value of the final integral, because when we did the bootstrapping, we took resamples from the distribution over a times b rather than resampling values for the final integral directly. Hopefully, this bootstrapping method is now reasonably clear. To summarize, the essential idea of the technique is that we perform some numerical experiment multiple times and extract a sample mean or mean. Calculating these sample means in this way gives us the parameters of some easier to sample distribution. We can thus assume that the sample means we got in the first step are the parameters of this distribution, so that we can extract resamples for the sample mean by resampling from the easier to sample distribution. We can then use the resamples we obtain to extract confidence limits. In the video, I've explained how this is done if we are fitting the parameters of a Bernoulli distribution. The bootstrapping technique is not just limited to Bernoulli distributions, however. You can also use this method to get confidence limits on estimates of histograms and many other types of more complex random variables. To consolidate what you've learned in the video, however, you will in this next task use this method to calculate error bars on your estimates for the area of the quarter circle by using the bootstrapping technique that resamples from the Bernoulli distribution that was discussed here. Good luck.